Together we're going to solve a problem on titration. Once again, we'll start by looking at the information given to us and underlining important pieces. Our medication has been ordered as an IV. That makes us think that we'll probably be calculating milliliters per hour. The range is given to us in micrograms per kilogram per minute. Our patient's weight is given, and the concentration of the medication in our IV bag is given, and the fact that it's D5W tells us that it is definitely in an IV bag. We're going to start by converting the weight to kilograms. So we take our patient's weight, 154 pounds, and we multiply by 2.2 pounds per 1 kilogram, and our pounds cancels. Next we go to our calculator, and I take 154, divide it by 2.2, and I come out with an even 70 kilograms. Now I look at my first question. It asks me to come up with the milliliter per hour rate for the lowest dose. Going back to my available information, I'm going to start with the 0.5 micrograms per kilogram per minute. Both the kilograms and the minutes belongs in the denominator of the problem. Before I go further, I'll point out to you at the bottom of the video is a link to the factor method, which is an alternative method of completing the same problem, and you're welcome to click on that link to jump ahead in the video to that portion. For now, I'll continue with the dimensional analysis. First thing I'm going to do is multiply by the patient's weight of 70 kilograms. That will cancel out the per kilogram. Second thing I'm going to do is to try to cancel the minutes. So I need that on the top of my fraction. I know that there are 60 minutes to 1 hour. And that changes my label to hours, which is one of the labels that I want. The order is in micrograms, but in my IV bag there are milligrams, so I need to convert. So there are 1,000 micrograms, and this conversion is on your conversions to memorize sheet to 1 milligram. Micrograms cancels. Now I need to change milligrams into milliliters, and the only way for me to do that is with a concentration of medication, and that is given to me on the bottom of my fraction. I'm going to use 50 milligrams. On the top of my fraction, the 250 milliliters. I always have to keep these two numbers together because they are in the same IV bag, so they are together in real life. All of my conversions are done. My remaining labels are milliliters per hour, which is the label I was supposed to find, so I'm ready to go to my calculator. Starting at the beginning of my problem, 0.5 times 70 times 60 times 250. Then I'll divide by everything that's on the bottom of my fraction, so divided by 1,000 and divided by 50. I have my final answer of 10.5 milliliters per hour. Milliliters per hour is normally rounded to tenths, and this answer came out to the tenths, so no rounding is necessary. The next problem asks, at what milliliter per hour rate will you set on the IV pump for the highest dose? So that means that we are going to repeat the same problem, but start with the 1.5 micrograms per kilogram per minute. I notice that the conversions are identical because I want to go to milliliters per hour. So I'm literally going to copy the exact same conversions from my previous problem into my new problem. It's now time to do our calculations. So I'll start by entering the 1.5 in the calculator, multiplying by 70, multiplying by 60, multiplying by 250, dividing by each piece of the denominator, so dividing by 1,000, and then dividing by 50, and I come up with an answer of 31.5 milliliters per hour. Again, it is an answer to the tenth, which is how I normally round, so no rounding is required. Now, some alternative approaches. First, we have with titration an equation D equals KR. D is for dose, K is a factor number related to the problem, and the patient, R is the rate. Typically, we find the K value after we find the minimum amount. So here where we found the lowest rate from the lowest dose, we fill those into this formula. The lowest dose is 0.5. K is unknown to us at this point. The lowest rate is 10.5. To solve this equation, I'll take 0.5 and divide by 10.5. When we're working with a factor number, we typically round our factor number to the hundredths place, which is 2 decimal places. So looking at the factor number, I have 0.05 because the 7 rounds the 4 up. So the K value is 0.05. Once I know the factor number, I can use the factor number to calculate the maximum. So using the K value that I have and using the D equals KR formula, I go to the second half of the problem. In the second half of the problem, the dose is known to be 1.5. K is known as 0.05. And the rate is unknown to me. In order to find the rate, I'll need to divide both sides of my equation by 0.05. So 1.5 divided by 0.05. This gives me an answer for rate of 30. Now you'll notice immediately that this is not the same answer as that I had before. The reason why these two answers are not an exact match is because we rounded the factor number. When we found the factor number, it was a long decimal, and we rounded it following standard protocol to hundredths, but that rounding changed the maximum slightly. Your test is set up to accept either answer, so you can use the dimensional analysis and calculate the exact answer, or you can use the factor method and get a close enough approximation to the exact answer.